Hello everyone. Today I'll be talking about the third part of chapter 1 chemistry A level for IG, the chemical formula and moles. As usual, I'll provide a link to download the material and the link of the website. The stoichiometry of a reaction. For any number of grams that reacted together, I can obtain the number of moles, and from the number of moles I can deduce the stoichiometry of a reaction. So if I have something like two hydrogen atoms reacting with oxygen to give me water, so from this chemical equation I could see that I have 2 moles of hydrogen reacting with 1 mole of oxygen to give me 2 moles of water. Let's take an example. If I have 56.2 grams of silicon that reacts with 284 grams of chlorine to give me 340.2 grams of silicon tetrachloride, use this information to calculate the stoichiometry of the reaction. So the first step would be writing down the chemical equation. So I have silicon reacting with chlorine to give me silicon tetrachloride. So second, I need to identify the relative atomic mass and the molecular mass for each one of them. So relative atomic mass of silicon would be equal to 28.1, and the relative molecular mass for chlorine would be equal to 2 multiplied by 35.5, which is the relative atomic mass for one chlorine atom. This would be equal to 70. The third would be the relative molecular mass for silicon tetrachloride. So I have the silicon, which is equal 28.1 plus I have 4 chlorine atoms, multiplying each one of them multiplying by 35.5 to give me this would give me 170.1. So second part would be converting the grams of each part of those into moles. So the moles of silicon would be equal to, I have here the given data, which is 56.2 grams multiplied by, if I have each 1 mole of silicon actually contains 28.1 grams of silicon. So the answer to that would be equal to moles. So I could see here, if I cancel this unit with this unit, I end up by the desired unit. Then I would calculate the moles of chlorine, which would be equal to the grams, the given information, which is 284 grams, multiplied if 1 mole of chlorine gas contains 70 grams of chlorine. This would be equal to 4 moles. The third part, knowing the number of moles of the produced silicon tetrachloride, that would be equal to the given information, which is 340 grams multiplied by if 1 mole of silicon tetrachloride actually contains 170.1 grams of silicon tetrachloride. So this means I will have 2 moles. Now let's write the equation with its correct stoichiometry. So I write 2 moles of silicon that would react with 4 moles of chlorine gas to give me 2 moles of silicon tetrachloride. Percent composition by mass. So the formula of a compound and the relative atomic masses can be used to calculate the percentage. If I know, if I needed the percentage by mass for any element in a certain compound, I can multiply the number of atoms by the molar mass of the element divided by the molar mass of the compound multiplied by 100. Example, calculate the percentage by mass of carbon in ethanol. First I need to calculate the molar mass of ethanol, which is equal to by 12, because I have here 2 atoms, plus I have 6 hydrogens. Here is 5, and here is the other one, which is total of 6, plus I have 1 oxygen, 1 multiplied by 16, and the sum for that would be equal to 46. Now the percent composition of carbon would be equal to, I have 2 atoms of carbon multiplied by the molar mass of carbon, which is equal to 12, divided by the 46, the molar mass of the whole compound. This would be equal to, and I will multiply by 100. This would be equal to 52.2%. Empirical formula. The empirical formula is the simplest whole number ratio of the element present in one molecule or formula unit of the compound. As for the molecular formula of a compound, it shows the total numbers of atoms of each element present in a molecule. The formula, the empirical formula, something like if I said hydrogen peroxide, so I know that the hydrogen peroxide is equal H2O2. This is the molecular formula for hydrogen peroxide. The empirical formula for hydrogen peroxide would be the simplest ratio between the hydrogen and the oxygen. So if I divided this by 2 and divided this by 2 would give me HO. So the empirical formula of hydrogen peroxide would be equal to HO. The formula of ionic compound is the same the empirical formula. So if I have something like NaCl is an ionic compound, so this ionic compound it have the same empirical formula is similar to its ionic formula. The percent composition enable us to determine the empirical formula of the compound, thus identifying the compound experimentally. So if I have the percent composition that we calculated in the previous slide, I can use it to identify the empirical formula of a certain compound. So predicting empirical formula from percent composition would be, the steps for that would be, if I know the mass percent, I can convert grams and divide by molar mass to get the moles of the element, and dividing by the smallest moles of the smallest number of moles to get the molar ratio of this element. Then I can change to integer subscript to get my empirical formula. So let's take a look at some examples. So first compound is calcium chloride. So its empirical formula would be calcium. So it's easier to write the molecular formula, and from the molecular formula I can write the empirical formula. So calcium chloride. So I have the same empirical formula similar to the molecular formula because it is an ionic compound. Water, which is H2O, is non-ionic compound, and it also have same ionic empirical formula similar to the molecular formula. The third one is carbon dioxide. So I have carbon dioxide, which is inorganic compound, and I have the molecular formula is equal to the empirical formula. If I looked at something like butene, butene is its formula is C4H10. If I divided this by 2 and divided this 10 by 2, this means my empirical formula is equal C2H5. Now let's move to use the composition by mass to deduce the empirical formula. Example: the composition by mass of hydrocarbon is 10% hydrogen and 90% carbon. Deduce the empirical formula. So now I know the percent composition of each part of this compound. Now I need to know what is this empirical formula of this compound. So if I write here carbon and I write here hydrogen, so I have here 90% and I have here 10%. So my first step would be dividing by the relative atomic mass for each one of them. So if I divide the 90 by 12, it would be equal to 7.5, and I will divide the 10 by 1, would be equal to 10. My second step will be simplify. I have to, so it is like a ratio, so I have to divide by the smallest number, which is, I have to divide by the smallest number, which is 7.5. So if I divided the 7.5 by 7.5, it would be equal to 1. But here the 10 would be divided by 7.5 would be equal to 1.3. Now I have the ratio between the carbon and the hydrogen says it is 1 to 1.3. I have to get rid of this fraction. I have to get a whole number. So to be able to do that, I have to try to multiply first by 2, then by 3, and moving on until I get a whole number. And I will use this number to further multiply it. So if I try 2, I will still have a fraction, but if I use 3, I will have here a whole number. So if I multiply it here by 3, this would be equal, this part would be equal to 3. So I multiply here by 3, 1 by 3 is equal 3, and 1.3 multiplied by 3 is actually equal to 4. So now I got a whole number in both parts. So the empirical formula would be equal to C3H4. Another example. In this example, I have 1.55 grams of phosphorus is completely combusted in the presence of oxygen, and 3.55 of an oxide of phosphorus is produced. Deduce the empirical formula of the oxide. So if I know now that this oxide is actually would be phosphorus plus oxygen to give me phosphorus oxide. So if I know here how much phosphorus is present, 155, and I don't know how much oxygen in that part, but I know here that I have these grams of phosphorus oxide. So I can, if I subtract 1.55 from the 3.55, I can know how much oxygen do I have. So first part, if I write down the ratio between the phosphorus and oxygen, so the phosphorus is actually equal 1.55 grams, and for oxygen it would be equal 3.55 minus 1.55, which is equal to 2 grams. Now I need to divide by the relative atomic mass of each one of them. So the 1.55 would be divided by 31 for phosphorus, relative atomic mass of phosphorus, and this would be equal to 0.05 mole. The other one, if I divided 2 by the relative atomic mass of oxygen, which is equal to 16, it would be equal to 125 mole. Now I need to divide by the smallest figure. So the smallest figure in that case would be this number. So divide by 0.05 each part of them. So 0.05 divided by 0.05, this would be equal to 1. But in that part, 0.125 divided by 0.05 would be equal to 2.5. Now I have here 1, but I have here I have here a fraction, so I need to multiply multiply first by 2. So if I try to multiply here by 2, it will give me a fraction. If I try 3, it will also give me a fraction. The only number will get me a whole number is multiplying by 4. So I have here to multiply by 4. In that case, 1 multiplied by 4 would be equal to 4, and for this part 2.5 multiplied by 4 would be equal to 10. Now I have 4 against 10, so my formula would be equal to B4O10. But I have to remember that when I use empirical formula, I have to simplify my numbers. So I have to divide here by 2 and divide here by 2. So my empirical formula would be equal B2O5. Now moving to the molecular formula. Like we said before, the molecular formula would show the actual number of each part of each of the different atoms present in the molecule. We can detect the molecular formula also from the empirical formula this time. Let's take an example. A compound has empirical formula CH2Br. Its relative molecular mass is 187.8. Deduce the molecular formula of this compound. So first I need to calculate the relative to find out the empirical formula mass. So the mass of empirical formula would be equal to, I have 1 carbon plus 2 hydrogens, 2 multiplied by 1, and I have the Br is equal to 79.9, and the sum for that would be equal to 93.94. Second part will be dividing my the molecular formula that I have here by the empirical formula. So divide the molecular formula by the empirical formula would be equal to, so I have to divide 187.8 divided by 93.94. This would be equal to 2. So this means I have this empirical formula, I have to multiply it by 2 to be able to get the molecular formula. So if I multiply it, the whole formula, which is CH2Br by 2, so it would be C2H4Br2. So this is my molecular formula. Another example, I have here 3 compounds and I know their molecular formula. I need to calculate or deduce the molecular formula of each one of them. So if I know the empirical formula and I have the molecular formula, if I calculated my empirical formula, the mass of my empirical formula, then find out the ratio between the molecular formula and the empirical formula, I can deduce my molecular formula. So number A, my empirical formula would be equal to, I have 3 carbons, 3 multiplied by 12, plus I have 5 hydrogens, each one is equal 1. So the sum for that would be equal to 41. Then I will find the ratio between the molecular formula and the empirical formula would be equal to 82 divided by 41, which should be equal to 2. So it is equal to 2. This means I have to multiply my empirical formula by 2. So C3H5 by 2 would be equal to C6H10. Number B, Cl3. So first I need to know my empirical formula, which would be equal to 12 plus 3 multiplied by 35.5, my relative atomic mass for chlorine, and the sum for that would be equal 118.5. Second step would be finding the ratio between molecular formula and the empirical formula. So my molecular formula, which is 273 divided by 118.5, and the ratio is equal to 2.3. I have to approximate this one, so it's approximately equal to 2. So I have to multiply my empirical formula by 2. So CCl3 multiplied by 2 would be equal to C2H6. Number C, CCH4. So I have to calculate my empirical formula, would be equal to C, which is equal to 12 plus, I have 2 hydrogens, H is equal 1, and that the sum for that would be equal to 14. Now if I try to find the ratio between the molecular formula and the empirical formula, it would be equal to 112 divided by 14, and this would be equal to 8. This means I have to multiply my empirical formula by 8, so CH2 multiplied by 8 would be equal to C8H16. Chemical formula and the chemical equations. For chemical formula of ionic compounds, it can be deduced from knowing the charge on each ion. I have 18 groups in the periodic table. The first group carries 1 positive charge. The second group carries 2 positive charges. As for group 17 till 15 till 17, it carries the number of the charges is actually 18 minus the number of the group. So if I wanted to know the charge on this on the group 17, I write 18 minus 17, which is equal to 1. I have to remember that groups from 15 till 17 is negatively charged. For 16, so if I write 18 minus 16, it would be equal to 2, and this is also a negatively charged group. So it has 2 negative charges. For group 13, all of them carries 3 positive charges. Transition elements usually varies. So I have something like iron. It can be it can have 2 positive charges, and also it can carry 3 positive charges. Write down the formula of each of the following compounds. Sodium nitrate. If I know that magnesium nitrate, so if I know magnesium is equal to positive 2 and the nitrate NO3, which is negative 1. I need the sum for that to be equal to 0 because I have electrical neutral compound. So in that case, I would write magnesium. I will need only 1 magnesium, and nitrate I will need 2 nitrate. Multiply this by 2 to be able to get the neutral charge. So magnesium and NO3 to be by 2. Second one, sodium sulfide. If I know that sodium is equal to positive 1 and sulfide is equal to negative 2, so this means this here is positive 1 and the 4 here to be negative 2. To be able to get 0, this means I have to multiply the sodium by 2. So my formula would be equal to Na2S. Naming ionic compounds. So the rule for naming ionic compound, first I have to name the nonmetal. I end the nonmetal name by IDE. Let's take an example. If I looked here, sodium, so I write sodium. The metal part doesn't change, but for the non-metal part, I will write IDE at the end of the name. So it will be sodium chloride. Second rule, if I have metal that carries more than 1 charge, we add Latin numbers. Let's look here. I have here iron, which is with valency is equal to positive 2, and I have here iron with which is equal to positive 3. In the first case, I would write iron, and I will write 2 between two brackets, and I will write the second part, which is the chloride. For that I would write iron, and because it is I have the valency is equal to positive 3, I will indicate the valency by writing these Latin numbers between brackets, and I will write the other part, which is the non-metal, with the end of IDE. Compound containing oxygen, we will end the name by ATE. Like in that case, I have here sodium, and I will name this part nitrate. As if I have more than one metal atom, I should add a prefix in the beginning of the name. So if I have 2 sodium atoms, in that case I should write diasodium sulfate. Example, name each of the following compounds. In that case I have here 3 sodium, so I write sodium phosphate. I have here 2 ammonium, so I write ammonium sulfate. The third one, it's aluminum, and because aluminum is actually trivalent, I write here 3 chloride. And for calcium it is equal to positive 2, so I write calcium, and I write 2 between two brackets nitrate. My next video would be the last part of chapter 1. Thank you and goodbye.